So I think this is the end of this morning session. And
I have one more question.
sorry, I didn't see.
Oh, okay.
Okay, please.
This is a question addressed maybe not to speaker, but to everybody. So my understanding on singular cosmologies like Genesis or Bounce have problems at the stability level. On the other hand, the standard inflationary cosmologies can be easily constructed in a stable way, for example, in the Hardensky context. What are the serious reasons to abandon standard inflation in favor of non-singular cosmologies? So so could somebody summarize the argument in a couple of sentences? Why Genesis or Bounce are definitely better than standard inflation? This is my question. Maybe Valery, or maybe Alexander, or maybe somebody else, because this is really. I'm reading the papers of Valery and company, and I understand what they do, but I do not really understand why they do this, because it's really difficult to construct stable non-singular cosmologies, but it's much easier to construct stable inflationary cosmologies. Maybe I'm missing.
Well, if you ask myself, if you ask me, Mikhail,
yes,
then my attitude is that even if you have very good theory, which is inflation, still it's worth having alternatives to see if they can really work, if they can produce anything compatible with observational data, and in the end whether they have some features which distinguish them from inflation. So this is just curiosity. I don't think inflation is
I understand,
bad.
But so inflation is not bad. So stable inflation remains.
For me, it's not a bad idea. It's a nice idea, but it's always nice to have a set of ideas to compare, set of models to compare one and another.
Okay. Thank you.
By the way, I can probably add another very small motivation on top of just need to compare inflation versus something else, because otherwise we wouldn't even know basically whether it's the only solution or not. There are, I think, 2 points. One point is that except of very nice original Starobinsky inflation and Higgs inflation, other models are getting more and more baroque and complicated in inflation, right? So for example, m squared, phi squared, everybody would buy. Lambda phi to the 4, everybody would buy. That was very beautiful and nice. But then if you go to fit current data, it becomes more and more complicated, except of the actually oldest model, which is still there. And the one which is basically suggested by Fede and Mischer. And which is actually very good that there are still these 2 simple models which still work. But nevertheless, it would be nice to see whether it's possible to have anything at all, as exactly as Varela and Anatolich said. But then there is another motivation, which I think is also very interesting. In normal setup, in inflation, without inflation, you go in the past, you necessarily hit quantum gravity regime. So basically, your curvature at some moment will be strong. And that implies that early universe could provide you kind of knowledge about quantum gravity. Maybe indirectly, maybe in some way, but whatever. Maybe it's not feasible in observationally, but at least in whatever, 1 billion years, you could do it. But if you had a genesis, for example, or a bounce, and the bounce was not strong, then this provides a completely different perspective. In that sense, looking in the past, you would never see quantum gravity at all. You would see this gravity modification or some stuff, but not quantum gravity. Never Planckian curvatures. And that's ideologically very, very interesting, because that's very different from normal inflation.
Yeah, there was also motivation given by Young Kai in his talk right now. So, some people think that swampland ideas actually sort of rule out inflation. I mean, it's not. I don't buy this, but some people do.
Yeah, yeah, no, that's true. But you see, with this, it's a kind of funny story. So I remember once talking to Rafael Busa, and he told me, "Look, I would not give any single dollar to people who try to investigate dark energy because we all know it's cosmological constant, right?" But the point is, now this swampland conjecture actually excludes cosmological constant because it excludes any positive minimum, and that's it. And it's pretty funny because the same Rafael was saying me that prediction of existence of cosmological constant using the anthropic principle is a major achievement of string theory, and now swampland actually does not allow you to have it at all, never. And the point is, then they would need to resort to some quintessence or something very, very, very different. So therefore, I don't know what to think.
You mean actual inflation, not the present day inflation, not the primordial one.
Well, you see, that's exactly the point. But because if you formally apply this conjecture or this swampland conjecture, then effectively the current lambda is your minimum of, let's say, the only, well, of all these moduli fields together. I don't know what they think there, right? And this conjecture is saying you that your potential can never be positive. I mean, it's the minimum. So that's why it's pretty funny.
Mikhail, both today and inflation, both today present cosmological constant, if it is cosmological constant, and inflation in the past with 60 foldings are in contradiction with the swampland conjecture.
Right. Yeah. But I think originally, as it was formulated at the very beginning, even normal Higgs was in contradiction, because they would not even at the beginning allow the top of the potential to be there too, which was so basically even the top of the potential is not allowed to be positive, which would be a bit too much. So therefore, I don't know what to buy out of them. They need to they need to either sell it well or.
So okay, this means that the original idea of primordial inflation is still with us in the form of Starobinsky inflation or Higgs inflation. But for people who want to avoid quantum gravity regime, or just for people who are curious, it's nice to study alternative scenarios like Genesis. Is this correct?
Right, but also completeness. You see, completeness. It's also very, very good argument, because inflation is not past completely.
I see.
So
but Valery, concerning your remark about null geodesics, I think in general relativity there is notion of null completeness, because when, well, it's with respect to null geodesics in particular. It's done, not with anything else.
Yeah, but the problem is that there is no. I don't think there is good physical reason behind this notion, because the affine parameter is not something that you can measure.
Right, but Penrose diagrams, after all, are constructed.
Yeah, but however, if you do conformal transformation, you can easily convert geodesically incomplete into geodesically complete.
Oh, really?
Yeah, of course.
Because
of course, I mean, National Friedman-Robertson-Walker theory with singularity at a equal to 0, at time equals 0, you make conformal transformation, and after conformal transformation, you end up with Minkowski. And in both,
in this sense.
yeah, and your photons or gravitons live in either of these two metrics. They don't care.
Oh, I see. Yeah. In this sense. Okay. Okay. Thank you, everybody, for for this little discussion. Yeah.
Thanks for asking it. That's good.
Well,
Look, this would be better
okay.
for the banquet, but they don't have banquets, so therefore.
Well, maybe one should organize online banquets. So it's a banquet of you know of spirit.
Next year.
Of soul.
Come to next Quarks. There we will have a banquet, definitely.
Yes.
Okay.
Looking forward.
Okay, so thanks a lot to everyone, the speakers in particular. And I think we can close the session now. And the next and final session will be at 4 p.m. Moscow time, a bit later. So thank you, everyone.
Thank you, David, for sharing.
Thank you. Bye.